And we're going to show a real good example of using Octera ML for proactive data center congestion. So the first demo is proactive detection of data center congestion. And we'll start with a very simple kind of data center construct. In this case, we actually have ESXi servers connected through a Dell MX fabric, if you will, to Dell PowerStore node. This is actually from a live environment that we have running, and it was a nice example we could illustrate today. Octera is collecting data from this. It's collecting stuff from the servers through SNMP. It's getting flow data from the MX switches. In this case, the power stores don't have a lot of capability for telemetry. And so we're actually somewhat blind to what they're doing, but we'll show you how we can get a sense of health to them. Now, the scenario is things are running well. As happens, they added a new workload to support a new application. This application puts a load in the system. And the expectation is this new load will be fine. But of course, things aren't always fine sometimes in the real world. And we get a bunch of unexpected congestion. We detect this using retransmit data from SFlow. So we're passive in the network. We notify the operator. And the operator then uses that notification as a springboard to our software. We actually do more analysis to go figure out, okay, who is this impacting, what applications, and then understand more of the root cause. Is it my servers that are dropping stuff? Is it my fabric? Is it something else? So that's the demo we're going to show. This works. This is one of our main use cases for data centers. We have several of these in production, of course. This is a nice one I could show. It was when I was working that I can demo. So we'll show that right now. It's a video, which I'll narrate. So we have Slack up. We get a notification. You've seen this before in the previous sessions where it shows that there is an issue with TCP SAC. So normally, if the network's running clean, we should not have any packets with the SAC option set. If it's running poorly, we see these. And so in this case, the operator clicks on the link in the anomaly, and they go to our dashboard where you see the anomaly in detail. And that's what we're seeing right here. You can see it's happened at midnight. The anomaly happened. It went away for a little bit, and it came back again. So these are consecutive anomalies. Each of these lines become a additional anomaly, saying we're still in an anomaly state. Now, the operator wants to go investigate this anomaly because it is important to them. This is the running production workloads. So what they've done first is they went from the anomaly view to an analytics view on our product. And again, it's the exact anomaly you've seen in a time series data. This agent IP reflects the switch IP address. So the first thing they want to do is sort all this data by TCP SACs, because that's the signal we're getting that tells us there's a problem. The next thing they understand is, all right, I have SACs on a switch, but I don't know what IPs are causing these things. Like, what do the IPs actually have these in their data stream? So what they're going to do build is ad hoc, add these dimensions or classifications of data to the right-hand side. So the operator knows what they want to find out. And they do this right now, real time in our software. What the operator does is they know what they're looking for a little bit here. They add these in here. And so as you can see, we're rebuilding this graph in real time, basically, as they add dimensions. Because what you don't maybe notice is I've sorted all this data by top talker is my TCP SAC. So the top IP address here is a top IP that has SAC retransmit, top source port, top destination port. Now, what I can quickly see now is that there's one destination port. I'm going to go back and pause it here because I think it's important to understand that there is right here. There's one destination port that sticks out. All these SACs are happening to 4420. There's a handful of destination IP addresses and only 2 source IPs or 3. This is the switches talking to the power store node. So I have a congestion issue in my fabric that's actually problematic for my application right now. So now, this is, again, this was not our lab, but somebody else's environment. What they did is they built dashboards for their server fabric, or their servers rather, and for their fabric. And so what they did, first thing they did is they go, all right, let me look at the health of my server. They built a dashboard. This is their dashboard. What you're seeing here is in octets, out if out discard ratio. So actually look at the ratio of discards to total traffic. As they scroll through there, you can see that spike in traffic up here. That's what caused the actual anomaly in the switch fabric. If you look at your discard ratio, it actually goes down. So when traffic goes up, we're not discarding more packets. The ratio is actually less. But my actual discard count spikes a little bit, but in relation to my traffic, it's very, very minor. So in essence, I know my servers are running pretty clean because I am not dropping packets there. So now what they would do is they scroll down to their Fabric view of the dashboard. And again, Slack was what started this whole thing. That's how the operator even knew to come here. In this case, I'm seeing the different TCP flags of my Fabric. I'm also seeing that same traffic peak we just saw up top, but in the view of the Fabric. But now as I scroll down, even more what you'll see is that I'm dropping a ton of Fabrics, ton of packets in my Fabric. Look at my discards here. It's in the 20 million. So now I know that this is my issue. My Fabric is dropping packets exponentially. My servers are actually doing pretty good. And so that's good to know, but I still don't know what interface my Fabric's even causing or maybe understand more about it. So now the operator goes from that kind of Fabric dashboard to a more detailed view. This is where the power of our analytics is. Like, they're building these things ad hoc. I say, I want to see it by device name. So he puts that in a column up here. And he kind of looks at data. These are the two devices that are causing this issue. They're having this issue. But what's interesting now is we look at this. There's actually one device, one switch is causing twice as many as the other switch. So now I know I have a bigger problem, MX01 than I'd have an MX02. And for the sake of time, I'll kind of try to keep this a little bit fast forward. Is what we do is we figure out that there's actually a load balancing issue in the Fabric. That one interface is taking on more than the other one, and that extra couple hundred megabyte is causing the discard 2x the number of drops. And so the operators are really quickly to hone on to that and say, all right, here's actually my issue in the network. It's load balancing on my MX Fabric. The whole kick off this thing, though, was obviously ML using SAC trade data in S flows. This works across different flow types. This is just one example. But it's a pretty neat one, and it works across data center fabrics. There's a topology that goes on this example too.
In this video, we are investigating an application that is having performance issues. In this scenario, the application team or customer has reported the issue to the NOC. We want the operator to spend as little time as possible to determine if the network is innocent, and if not, what the problem might be. To troubleshoot, we are going to use the Octera UI to map that application flow across the network. Using Octera automatic machine learning based anomaly detection, we can then show any anomalies along the path that were triggered at the same time. We start by accessing the Octera portal. We will use a topology view. First, we will set the time filter to the appropriate time. In our example, the incident happened on November 6th between the hours of 1200 and 1300. Next, we will select the tuple that matches the application flow. In our example, we are inputting all 5 tuples, but in some cases we may use fewer. Note that commonly used tuples or regex expressions can be saved for quicker analysis. Once the tuple is entered, the topology will highlight the network devices the flow passed through. Now that we have set the appropriate time filter, we will configure Octera to display any anomalies along the path at the configured time. Devices in the flow path with anomalies will be highlighted in red. You can click on the anomalies to see more details about the events. The ingress switch has a significant increase in the buffer count. By adjusting the time series scale, we can clearly see the deviation to the pattern. At the same time, the egress switch has an anomaly on its interface out discards. Again, expanding the time series allows the pattern to be easier seen. Selecting past anomalies will show when the first anomaly was detected and how long it has been happening. With this data, our operator has confirmed that the application was impacted by the network on both ingress and egress ports of the Fabric. You can watch the video, Proactive Network Brownouts, to solve application performance issues, to see how to use Octera to identify offending flows that are impacting the network. Thank you.